There exists a very useful relationship between the electric flux passing through a surface and the amount of charge that this surface encloses. To see this, we attempt to calculate the electric flux through a spherical surface that encloses a point charge. We know that the direction of the electric field will change between different points on the spherical surface because the electric field produced by a point charge is radial. Therefore, in order to calculate the electric flux, we need to divide the spherical surface into a number of tiny surfaces, each characterized by a tiny surface or area vector dA. We know that if we choose these surface elements to be small enough, the electric field variation across this surface will be negligible. And to a good approximation, we therefore can say that the electric field passing through the little surface element dA is uniform, and if the surface element is small enough, to a good approximation, the surface itself is flat. So we can calculate the electric flux passing through this tiny surface element dA. We know the electric flux is given by the dot product of the electric field and the area vector. Because the electric field is radial, we expect it to be perpendicular to the spherical surface at all points on the surface. By definition, the area vector itself is perpendicular to the surface it describes. So this simplifies the dot product to simply being the multiple of the electric field magnitude and the size of our infinitesimal surface area dA. To get the total flux through the entire spherical surface, we must now add up all the tiny contributions to the flux through all the tiny surface elements dA. And this just results in an integral over the quantity EdA. We can simplify this further by noting that the electric field produced by a point charge has got the same magnitude for the same distance away from the source charge. Therefore, if we evaluate the electric field at all points on a spherical surface, which are equidistant from the source, we know that the electric field magnitude will be constant, so we can take it out of the integral. What we're left with is the surface integral of all the tiny elements dA, which literally means we must just add up or sum together all the tiny surface elements dA, and we know that if we do this, all these tiny surface elements will add up to the surface of the sphere, which in this case is 4 pi times its radius squared. We also know that the electric field produced by a point charge is given by the expression shown on the screen. So, if we substitute in this for the electric field, we find a very simple relationship between the electric flux and the charge enclosed by this spherical surface. And this is known as Gauss's law. Physically, it means that the electric flux that passes through a surface that encloses a certain amount of charge Q is just equals to the charge Q divided by a constant. And this law holds irrespective of the shape or the geometry of the surface, or where the charge is placed within that surface.